All right. Greetings, YouTube. Beautiful Mind here. And we are updating our lectures for Calculus for Business. We just got a new set of books. So, over the next few months, I'll be updating most, if not all, of my lectures. So, all right, let's hop into this. So this is Calculus for Business. So we're going to be using Calculus and its Applications, the third edition by Bittinger, Ellen Bogan, and Sargent and Kramer. And this presentation is from chapter R on functions, graphs, and models, starting with section R4, slope and linear functions. A few objectives: find and interpret the slope of a line, graph equations of the form y equals c and x equals a, graph linear functions, find an equation of a line when given the slope and 1 point on the line and when given 2 points on the line. And finally, solve applied problems involving slope and linear functions. So we have a definition here, which is a slope. The slope of a line containing the points P1, which is x1 and y1, and P2, which is x2 and y2, is basically your rise over your run, which is your change in y over change in x. So that's where the y2 minus y1 over x2 minus x1 comes from. Again, that's the change in y over the change in x. So slope in a practical sense is like how steep a line is. So, in your everyday life, you might see it, if you could think about a hill, the more steep the hill is, the higher the slope. The more flat it is, the lower the slope. Down like a complete flat surface, like, just a flat plane, that has a slope of 0. And like a cliff, it has a vertical, like sheer cliff, the slope there is actually undefined. But the more steep the hill is, the higher the slope. Okay. So find the slope of a line containing these 2 points. So basically we're just applying, I'm going to piggyback off of my prepared notes. I feel like, we don't have to go into heavy detail here, but I'll take a few notes. So if we want the slope of the line between 2 points. Now, one thing I like to do is whenever I get a set of ordered pairs, I'll go x1, y1, x2, y2, and just label it off the rip. And then also I like to include relevant formulas. So for instance, in this case, since we're doing slope, change in y over change in x is going to be our y2 minus y1 over x2 minus x1. This is our slope formula. Okay. So then if we plug in, now when I'm doing my substitutions for each component, first I'm going to replace each component with a blank set of parentheses. So I'll go, this is my y2 minus my y1 over my x2 minus my x1. And the parentheses basically just help us to keep track of our signs. So my y2 is 9, my y1 is 6, my x2 is negative 4, and my x1 is negative 2. Okay. So the numerator, 9 minus 6 is 3. The denominator, you have a double negative at play here. All right, so that's why we use our parentheses. Without the parentheses, oftentimes students lose. It's fairly easy to lose track of like signs. So the parentheses just help us to keep track of our signs. All right. Okay. So now we see it's a negative 4 plus 2, which finishes at a negative 2. So then the final result should just be a negative 3 over 2. So move some items around here real quick. This was our final result. Okay. And so anyway, so I was going to use my prepared notes. I just went on and did it. And so here's a typed version of the exact same thing that we just experienced. Okay. So in this example, find the slope of the line containing these 2 points. Similar thing. So I'm just going to actually use my prepared notes in this instance. Did I not? Yeah, here they are. All right, same deal, just different set of numbers. So I would encourage you to give that one a go. So here we're asked the graph y equals 4. Does the graph represent a function? Why or why not? What is the line's slope? All right. So y equals 4 means what? No matter what x value you choose, the output for y is always 4. So you can just choose like a few values of x. No matter what x you choose, y is always going to be 4. So for instance, like when x is 0, you can have the ordered pair 0, 4. You can have the ordered pair, 3, 4. Just choose a couple of values of x. If you plot those points and connect them with a straight edge, you basically get a horizontal horizontal line through y equals 4. Okay. So then does the graph represent a function? Why or why not? I would say yes, it represents a function. One way you can argue it is like using the vertical line test because it passes the vertical line test. So no matter where we draw a vertical line through the horizontal line, it'll only touch the graph once. So that means that every y corresponds to exactly 1x. We don't have one y corresponding to more than 1x. So it passes the vertical line test. So it is a function. And then the slope of this guy is going to have a slope of 0. If you were to take 2 points from your horizontal line that you drew and then plug them into the slope formula like we did in the previous couple examples, you'll get an answer of 0. Yeah. Okay. So here's a type version of that dialogue, right? So the graph consists of all ordered pairs whose second coordinate is 4. So again, no matter what x you choose, y is always 4. So just choose a couple of values of x. In this instance, just let the y be 4, plot the points, connect them with a straight edge. You see it off to the right in blue. So then the vertical line test holds, right? So they're using the same test that we used. It passes the vertical line test. So the graph represents a function since it passes the vertical line test. Since there is no change in y, the line slope is 0, right? So again, if we plug it into the slope formula, just take 2 points from our line. When you plug them in and calculate, eventually you get to an answer of 0. Okay. All right, so I think I'm gonna talk through this one as well. In this example, we're asked to graph x equals -3. Does the graph represent a function, y or not? And then what is the slope line, right? So in the previous one, we had like y equals what, 3 or 4 or whatever. What was the value? We had y equals 4. So in the previous one, we said what, no matter what x we chose, y was always 4. So we can do this one in a similar fashion. You can also choose values of y and then find the corresponding x. So no matter what y value you choose, x is always -3, right? So if you plot those points, you'll get a straight vertical line, right? So a vertical line through x equals -3. Does the graph represent a function? We will say no. A vertical line through x equals -3 is an example of a graph that fails the vertical line test because we can draw a vertical line and it'll touch our graph more than once. So that means that it's not a function. In other words, we have one y value that corresponds to more than one x value. So it's not a function. The slope of a vertical line is going to be undefined. And here's a type version of what we just experienced. So the graph consists of all ordered pairs whose first coordinate is -3. So no matter what y we choose, the corresponding x is -3. The graph does not represent a function because it fails the vertical line test. Since there is no change in x, let me see. I'm gonna get that to display a little bit better. Guess that's fine. Since there's no change in x, the line slope is undefined. Okay. Quick checks I usually leave for you. So I would encourage you to just attempt these. Do your best to try to do them without looking at the answer first. Just try to take the question, answer it yourself, and then compare your answer to their answer. The more you're able to answer these questions on your own with little to no help, the better off you are. Now if you need help when you're practicing, that's fine. But that repetition is what locks it into the memory, right? Practice makes absolutely not. All right. Hopefully you didn't say perfect or you weren't thinking perfect. Practice makes improvement. If it made perfect, we'd never have to practice again. And as humans, we all know what happens when we stop practicing. Our skill level goes down. So as humans, our abilities are we're either spiraling up or we're spiraling down, right? And so if we don't practice, we're spiraling down. If we practice, we're spiraling up. But we have moments of perfection, but you have to constantly be practicing to sharpen and grow and stay relevant and things of that nature. Okay. So practice makes improvement. Okay, so the graph of y equals c or f of x equals c, or a horizontal line, is the graph of a function. Such a function is referred to as a constant function. So the graph of x equals a is a vertical line and does not represent a function. Okay, so y equals a number is a horizontal line. We call that our constant function. X equals a number is a vertical line. It's not a function at all. So the graph of the function given by y equals mx or f of x equals mx is a straight line through the origin and the point 1, m. Here are a few various graphs of y equals mx for positive slopes. Okay, so you see it there on the left. And here are various graphs of y equals mx for negative values of m, or with negative slopes. So for a line, when we trace the line from the left to the right, if it goes up, that means the slope is positive. If we trace the line from the left to the right and it's going down, that means the slope is negative. All right, so we have this example on physical science. It says the weight m in pounds of an object on the moon is proportional to the weight e of the object on the Earth. Astronaut who weighs 180 pounds on Earth will weigh 28.8 pounds on the moon. Find an equation that relates the weight to the moon, the weight of the weight on the moon to the weight on Earth. And an astronaut weighs 120 pounds on Earth. How much will the astronaut weigh on the moon? Okay. So it says that the weight of an object on the moon is proportional to the weight on the Earth. So whenever we have that something is proportional to another, we can make an equation that should take the form m equals k times e, or k is some constant. Let me think. Yeah, I think it's just a constant. I'm trying to think if it's a constant or a positive constant, if it has to be positive. But it's usually, m equals k times e. We'll see it in just a moment. Okay. So let's see. Where's my pen? There it is. Okay. So let me see. The astronaut weighs 180 pounds on Earth and 28 pounds on the moon, so we need to solve for k. So again, m equals k times e. All right, and I'll just kind of work to the side because I'm a little short on space here. It says that they weigh this on Earth and on the moon. So if we have, for whatever reason I can't write, 28.8 pounds equals some k times 180 pounds. So then ultimately k should equal 28.8 over 180, whatever that number is. So then the weight on the moon should be equal to, again, whatever, and I'll just reference it right now as star. So whatever star is times their weight on Earth. Okay. So then they give us the weight on Earth. How much would they weigh on the moon? So then their weight on the moon is going to be, again, whatever star is times 120 to get our result, their weight on the moon. Okay. So let me see if I can get this going. It should be this one. Okay, I gotta find my file. Ooh, I think I got it here. Here, come on, you can do it. I believe in you. Try again, that one. Yeah, it struggles. Okay, I got it somewhere else. I gotta think about where else I have it. That one. Oh, come on. Oh. See if I got it here. Nope. Okay. Let me try this one. Okay, found it. Okay, yeah. I didn't really want to search, but we got it working. Okay, so that was the main thing. All right, sorry about that. So, I hadn't been using it. If I'm not using it, then I usually have to reload it or whatever. Anyway. All right, so we got it up and running. Okay, so let's crunch some of these numbers. So for instance, K, let's do 28.8. 28.8 divided by 180, 0.16. So our claim is that it should take on the form, I'm just going to do it like this. The weight on the moon should equal 0.16 times their weight on Earth. So then if the person weighs 120, so we want to take that 0.16 times 120, 19.2. Okay. All right, let's see how do we do. So this is just us kind of playing around. Let's see how do we do. Let's see the equation. Okay, so yeah, so the equation has the form m, basically the same thing. They just use m instead of k. It's just a label. That's fine. We got the same constant. All right, the 0.16. So the weight on the moon is going to be 16 hundredths the weight on Earth, where the weight on Earth and the moon are both positive, not negative, sorry. So to find the weight on the moon, 19.2, that's the astronaut who weighs 120 pounds on Earth, weighs 19.2 pounds on the moon, okay? Based on this dialogue. We're not getting into whether we've actually been to the moon or if we have been, what we discovered. We're not getting all that. Anywho, all right. A linear function is any function that can be written in this form, y equals mx plus b, or f of x equals mx plus b. Its graph has the same slope m as the graph of y equals mx and crosses the y-axis at the y-intercept, 0, b. The point 0, b is also called the y-intercept, okay. Y equals mx plus b is called the slope-intercept equation of a line. So here we asked to find, quick check, I'm going to leave that as an exercise for you. You should be able to handle it. I'm going to leave it. Find the equation of a line with this slope containing this point. Okay. So they give us a slope and a point. We have another formula called the point slope formula. We typically use it when we're given a point and a slope. I'll just reference it. I don't necessarily want to use it right now. Point slope formula. So here, when working with lines, there are a few formulas we want to have ready to go. The slope formula, y2 minus y1 over x2 minus x1. All right, that's our slope formula. I'll label it as a slope. Okay. Another formula is our slope-intercept formula, which is the y equals mx plus b. Honestly, these are the only two you really need. You can get everything about lines with these two. This is our slope-intercept formula. And then there is a point slope formula. Y minus y1 equals m times x minus x1. All right. We use this when we're given a point and a slope. I'll leave that for you to discover how to use it on your own unless somebody requests it. But honestly, we can do everything with the first two equations. I'm going to minimize it and use it as a reference. Okay. So we have the slope. So what I'm going to do is plug this into y equals mx plus b. Again, we could start with the point slope and plug in the point along with the slope, finish with an equation, and then use algebra to get it to the form y equals mx plus b. I'm going to start at y equals mx plus b. So I'll start here. So if we have y equals mx plus b, right? Now we know our slope is 3. We're going to let our x be a -1 here. We don't know what b is just yet. And our y is going to be a -5. Okay. We have one equation, one unknown, so we can solve for b. Looks like we add 3 to both sides, and we'll get b equals -2. Okay. So we have our b, we have our slope. So then, again, if we want to finish with y equals mx plus b, we plug those components in. Y equals our slope, which is 3x. Our b is a -2. Okay. And I might showcase point slope a few times, but right. So when x, now we can check, right? We can see here we have it in the form y equals mx plus b. We see that the slope is 3. When x is a -1, the corresponding y should be a -5. So 3 times -1 is -3. Minus 2 is indeed -5. So that checks out. Just the type version of what we experienced. Again, this is called the point slope form of the equation. We alluded to it. We didn't use it, but we tend to use this when we're given a point and a slope. Styles, a clothing firm, has fixed costs of $10,000 a month. These costs, such as rent, maintenance, and so on, are paid no matter how much the company produces. To produce X units of a lightweight suit costs $20 per suit in addition to the fixed costs. That is, the variable cost of producing X suit is $20X dollars. These costs are due to the amount produced and include material, wages, electricity, and so on. The total cost of producing X suits in a month is given by the variable cost plus the fixed cost, which is the 20X plus 10,000. Graph the variable cost, the fixed cost, and the total cost functions, and then what is the total cost of producing 100 suits and the cost of producing 400 suits. So variable cost, okay, so the variable cost is the 20X, so that's going to be a diagonal line passing through the origin with a slope of positive 20. The fixed cost, it says, is 10,000 per month. So there should be a flat horizontal line through y equals 10,000. So then the cost function, it should be a diagonal line with a slope of 20 with a y-intercept of 10,000. Okay, and then what is the total, before we confirm those results, I'm going to go ahead and explore B. What is the total cost of producing 100 suits? So I guess we just plug it into our function, 100. So 2,000, so $12,000, and then 400, 4 times 2 is 8, so 8,000, so 18,000. So 12,000 and 18,000 for B. Let's see. So the variable cost, okay. Variable cost, a diagonal line through the origin with a slope of 20. Fixed cost is a flat horizontal line through y equals 10,000. The total cost, right? A wire is basically a straight line, right? So it's a y-intercept of 10,000 with a slope of 20. Okay, so that's fine. $12,000 and $18,000. Okay. All right. I think this might be the last example. When the business sells an item, it receives the price paid by the consumer. This is normally greater than the cost of the business of producing the item. The total revenue that a business receives is the product of the number of items sold and the price paid per item. So therefore, if Style sells 8 units at $80 per suit, the total revenue in dollars is going to be given by the unit price times the quantity sold, so 80 times X. So then if the cost function is 20X plus 10,000, we're asked to graph the revenue function, and the cost function uses the same set of axes. So the revenue function is a diagonal line with a slope of 80 passing through the origin. Again, the cost function is a diagonal line with a slope of 20 with a y-intercept of 10,000. And we should be able to see at least where they cross. So then the total profit that the business makes is basically going to be the revenue, total revenue minus total cost, or revenue minus cost. So we would take the 80X minus our cost function, the 20X plus 10,000, and we have to distribute that negative, so you have to watch out for that. The company will break even at the value for which the profit equals 0. So that's when your total revenue is going to be equal to your total cost. Okay. So we have our revenue function, the 80X. We have our cost function. It has a y-intercept of 10,000 with a slope of 20. So notice that it breaks the flat surface up into like four panels, and we have 2 regions that have like those acute angles. So you see the loss. They're at a loss when they're on the left side there, and then they're at a profit or a gain when they're on the right. So then where the revenue meets the cost function, that's the break-even point. Okay. So then to find the profit, we did revenue minus cost. Be sure to distribute the negative for it to behave properly. Okay. So the break-even point is at 166 2/3. So we don't turn a profit until we produce and sell 167th units sold. that's the first time we turn a profit. Anything below 167, we're not turning a profit. So again, we set the revenue equal to the cost. That's where the 166 and 2/3, so approximately 167 suits. Okay, that was fairly interesting. All right. So with that's just that's us making our way through section R4, and yeah. So with that, we're going to go ahead and end the session here. And from one beautiful mind to another, take care and peace.